Okay, welcome to lecture 3.10. Okay, here I'm just going to give you some hints on your homework. Okay, number one, it says use Newton's method to estimate lambda in assignment one. So go back to the Diermeier-Merlo uh, paper data. Um, Look at the spreadsheet you created. Okay, look at your, well, actually, remember how you estimated lambda and so on. And before, we may have used goal seek to estimate lambda, or just maybe trial and error. You got the optimal lambda hat by those methods. Now, what I want you to do is you to use your own hill climbing routine. Now, in usually in these hill climbing routines, you use the Newton-Raphson method, but we only have one parameter to estimate, so we're actually using Newton's method. And so, in particular, what I want you to do is I want you to recall. I can't remember the lecture I gave you, but we had you start off with a seed value for lambda, call that lambda 0. Sometimes, more generally, if it's a vector, we'll call it theta 0. But for this homework problem, it's going to be lambda 0. And I told you make it 0.5. Okay, so that's going to be your seed value. That's going to be your first guess. And then recall that formula, lambda t plus 1. And you know what? I don't remember it exactly, but I want you to go back. And it equaled lambda t. I think it was minus the log likelihood. Okay, remember this, log likelihood, not the likelihood. So little l prime of lambda t divided by little l double prime of lambda t. Like I said, I don't remember if that's exactly right. I'm effective. That might have been a plus sign. I think it was minus. But regardless, remember, so you've got lambda 0. So for lambda 1, you'll plug in lambda 0. So you should be able to write this formula in your spreadsheet because you've already computed the derivative and also the second derivative. Should I use the plus derivative or second derivative? If d is small, it shouldn't matter. Okay, and by the way, all of you will get slightly different answers, and it'll be slightly different from my answers I give you. If you're just slightly off, I know it's like the rounding error, or choice of D. Don't worry about that. But okay, you're going to use Newton's method. Technically, this is a special case of the Newton-Raphson method. So you're doing a hill climbing routine. So that is number one. Okay. Now, number 2 through 7, you're going to do the Levitt-Porter paper. Okay, so here first, what you're going to do, number 2, let Q equal the proportion of drivers who are drunk, and thus 1 minus Q is the proportion of drivers who are sober. Okay, the proportion of drivers who were drunk is, in Levitt-Porter's terminology, is ND divided by NS plus ND. Okay. And we're just defining that as Q. And I told you the answer that they find is it's about 0.2, at least Friday night at midnight. Okay. Now, here's what's going on. So in the Levitt-Porter paper, they had NS and ND, and they said we can't identify both of them, so what we're going to do is identify the ratio. I'm going to say, let's start over. Instead of defining N as the ratio of ND to NS, let's forget about that and instead use this Q. Okay, trust me, you can identify it, okay, with Q. So everywhere before where we put in these N's, I want you to start over. Start off with N and S, and then try to figure out how you can substitute Q's. Okay, you should be able to do this. Okay, so you'll rewrite a likelihood function. Levitt and Porter had the big N. I want you to be able to do it with Q instead. Okay. Okay. Given an interaction, what is the probability that both drivers are sober? Okay, so now suppose you have theta D and theta S. Okay. 2A, given an interaction, what's the probability that both drivers are sober and at least one driver makes a mistake? So that's probability eastbound equals S, both drivers sober, and westbound equals S, and crash. Okay, so use their terminology. So that's going to be it's going to be 1 minus q times 1 minus q times theta s plus theta s. Okay, it'll be something like that. Okay, so that's 2a. 2b, given an interaction, what's the probability both drivers are drunk and they crash? Okay, gonna be a similar term. 2c, given an interaction, um, what's probably one driver's drunk, one is sober, and a crash occurs. So this is just your theory. Okay, you're writing out your theory. 2D, given an interaction, what is the probability that a crash occurs? Well, it's going to be the sum of all those three different cases. Okay. By the way, don't forget, given an interaction, what's the probability that one driver is drunk and one driver is sober? Okay, remember what's probably exactly one driver is drunk. Well, there's two ways that can happen. The eastbound driver is drunk, the westbound sober, or the opposite. Okay, remember that. 3, use Bayes' rules and your answers to 1. Sorry, I made a typo. And your answers to 2 to calculate the probabilities given that a crash has occurred. Was the probability that both drivers are drunk, given that a crash has occurred? It's probably exactly one driver's drunk, so on. Okay, now try to use those. So Levitt and Porter already calculated those things, but I want you to do. But they did it as a function of ND and S. I want you to do it as a function of Q. Okay. Question 4: define lambda equals theta S divided by theta D. Okay. Levitt and Porter did the opposite. They defined theta with no subscript as theta D divided by theta S. And I told you it's approximately 8. So when this is going to be, at least at midnight on Friday night, that is going to be approximately 1/8. 1, 2. Okay. That's 4. 4. Rewrite the 3 probabilities from problem 3 in terms of lambda. Okay. Take the theta. Okay. So remember, same problem you're going to have. You're not going to be able to identify theta D and theta S, but we can identify the ratio, and we're going to define that ratio as theta S divided by theta D equals lambda. We can rewrite all those probabilities from 3 in terms of lambda and Q. Okay, you should be able to do that. Okay, suppose you collect data and find that out of n total 2-car crashes, N0 were cases where neither driver was drunk, N1 were cases where exactly one driver was drunk, N2 were cases where both drivers are drunk. Write the log likelihood function for these data. It should be pretty easy. All you got to do is figure out the new P terms, where instead you've got lambda and Q. The likelihood function is just going to be P dd times what did I say? N to the 2. N to the 2 is the number of cases where 2 drivers were drunk times P ds in 1 times P SS in 0. Okay, so remember here again, instead of A's like Levitt and Porter used, I'm just going to give you N2, N1, and N0. So that's data. Again, all you need is 3 numbers. That's all the data you need. Okay, next, number 6. Here is a good idea to do whenever you're doing these kind of complex maximizations of a likelihood function. You start off with some simulated data, some made up data. And what I mean by that is you pretend you know your parameters. So pretend you know the value of lambda and the value of q, and then generate some data, okay? Then once you've generated that data, estimate the likelihood function for that data, and you should be able to get approximately the same numbers you got for the numbers you assumed for the parameters. Okay, so more specific, let me state the problem. Number 5, number 6. Okay, suppose q equals 2. Okay, q and lambda are, okay, here's what we're going to do. Q equals 0.2, okay? So assume you know the true parameter, the true Q. Q equals 0.2, theta S equals 0.01, and theta D equals 0.08. Suppose you knew the true values. In Excel, simulate 10,000 observations. Determine in each whether a crash occurs, and if so, how many of the drivers were drunk. Specifically, assume with each observation that there is an eastbound driver and a westbound driver. Define a latent variable distributed uniform 0, 1 to represent the propensity for the eastbound driver to be drunk. Use Excel function rand left paren, right paren, okay, to estimate that. Okay, the eastbound driver is drunk if and only if the latent variable is less than Q. Okay. All right. Let's go back. This one's going to be hard, okay? So what you're going to do is you're basically going to have an Excel spreadsheet with 10,000 lines, okay? And then you're going to have column 1, let's call it X eastbound driver, okay? And then what you're going to have is another column where it's gonna equal, it's a uniform random variable. So call it U sub E, but it equals rand left paren, right paren. Okay, so X E. No. We're just going to call X sub E equals rand left paren, right paren. Okay. That is going to be some number between 0 and 1. And suppose it's 0.324. Okay. Then the next column is an indicator. Okay. Eastbound is drunk. Okay. and you want that the probability that the eastbound driver of being drunk to be 0.2. And so call this this is column A, and so this is A2. But this is going to be and I can't remember the exact formula, but that equals 1 if A2 is greater than, no, less than 0.2, 0 if A2 greater than 0.2 or greater than or equal, okay? However you like. So see what this is going to do. It's going to pick a random variable. If that number is less than 0.2, it's going to put a 1 in. So this is, that's cell B2. Okay. So you're going to now have an indicator variable in this simulated case, whether the eastbound driver is drunk or not, and the probability is going to be 0.2. You're going to do the same thing for the westbound driver. So XW is going to equal rand, left paren, right paren, and that's going to be C2. Then D2 is going to be an indicator whether the westbound driver is drunk or not. Okay. Create a second driver is drunk. Okay. Then you're going to have to write, so that's C2, and then you're going to have a D2 indicator if westbound is drunk. And then you're going to need to have E2, I'm going to call it F2. You're going to, E2 is another random variable. Say 0 to 1, and then you're going to create a F2, which indicates if eastbound makes a mistake. Okay, now this is going to be a little tricky. What you're going to have to do is look, you have your random number, that's going to be some number between 0 or 1. Then you're going to look to see whether eastbound is drunk or not. And then I said, I told you to assume that theta D equals 0.08, okay? So if in B2 you got a 1, okay, so that the eastbound driver is drunk, then you look to see whether the F2 is less than 0.08. Okay, that indicates whether he makes a mistake or not, given that he's drunk. On the other hand, what if he's sober? Okay, what if in B2 you have a 0 in there? Okay, we had theta, I told you theta S equals 0.01. Okay, so if B2 equals 0, then what you do is you look at E2, that random variable, see whether it's less than 0.01. If it's less than 0.01, then eastbound made a mistake. If it's greater than 0.01, eastbound did not. Okay, so it's a little tricky. So you're going to have F2 indicates whether eastbound driver makes a mistake or not. Okay, E2, and then you're going to have to do something similar. F2, FG2. G2 is similar random variable. GH2 is going to indicate whether W makes a mistake, whether W, the westbound driver, makes a mistake. Okay, once you've done that, you know what, you can do it either way you want. So Levitt and Porter said, well, let's do truth. Levitt and Porter assume the probability that either makes a mistake is the sum of those two values, and that's not exactly equal because there's an interaction term of the probability. Remember, they had theta I times theta j. They assume that always equals 0. You can make an assumption like that if you want. What I would do instead is say, let's look to see if H2 equals 1 or if F2 equals 1. So if either of them makes a mistake, use the OR function, then you've got a crash. Okay, so that's what you're doing. H2, I guess I2 will be the cell that indicates whether a crash occurred or not. Okay. And then I2, and then I2, J2. You can look whether there's a crash or not. Okay. If there's a crash, put a number how many of the drivers were drunk. So all you got to do is look in B2 and look in D2, sum those two variables. Okay, that's going to be 0, 1, or 2. Okay, then from those 10,000 observations, okay, what you do is somehow, it's up to you. You're going to be clever how to estimate these things. So out of those 10,000 observations, you're going to get something like 100 or 150 cases where there was a crash. Then I want you to be able to calculate out of those 150, say, cases, how many involved 2 drunk drivers, how many involved 1 drunk driver, how many involve 0 drunk drivers. Okay. Once you've done that, okay, you've answered 6. Once you've done that, out of the 10,000. You know what? I wrote on 6. Actually, that's fine. I said for the 6, let's do what I wrote. I wrote, out of the 10,000 observations, how many produce a crash? 6b. Of the 10,000, how many involve 0 drunk drivers? How many of the 10,000 cases, how many involve 0 drunk drivers? Of the 10,000 cases, how many involve 1? Okay. Okay, so that's a little bit easier than looking at of the crashes, how many. But you could do that too. Now, 7. Suppose you observe the following data. So with 6, I'm not asking you to do it, but what I'm asking you to do is like the warm-up exercise. If you really were going to do this as research, I would say try it first with some simulated data, and that's what you're doing in 6. You're doing simulated data. If you're really going to do this for the research, I would say, okay, now you've got your simulated data. Let's estimate the parameters given that simulated data. Let's estimate lambda and q. And you should get, if you did that, so if you've calculated the maximum likelihood value, maximize your likelihood function for lambda and found lambda and q, you should get q equals about 0.2 and lambda is about 1/8 because theta s was 0.01, theta d was 0.08. 0.01 divided by 0.08 is about 1/8. Okay, that is, your simulated data should give you about the same. Your estimate should give approximately the estimates that you asserted were true when you simulated your data. Okay. Number 7. Suppose you observe the following data. N0 equals 26, N1 equals 55, N2 equals 13. Create a spreadsheet in which you do a grid search to estimate lambda and Q. Okay, specifically, let lambda vary from 0.02 to 0.98 and equaling every value in between at an increment of 0.02. So 0.02, 0.04, 0.06, and so on, all the way up to 0.98. Do that both for lambda and Q. So you're going to have 0.02 to 0.98. I think that's going to be 49 numbers. So you're going to have 49 different lambdas, 49 different Qs. So you're going to have this huge table, 49 by 49. Okay, this is going to be a lot of grunt work, by the way. And this is, I've had students before say, "What can I do it in R?" The answer is no. Mr. Miyagi, you're doing wax on, wax off here, okay? So there are 49 for each combination. Compute the log likelihood, okay? So, you know what, I think the best let me give you a hint. When I tried it, I was able to do that special copy function in Excel where you put the cursor in the right bottom corner of the cell and you start doing copy. I could do that. I could set like lambda at 0.02 and then set Q equals 0.02, try Q equals 0.04, highlight those two cells, copy downward. I could allow Q to vary from 0.2 to 0.98 just using that copy function. But then I had to do it again. I couldn't figure out a way to make it easier. So what I had to do next is rewrite the same function setting lambda equals 0.04 and then try again. Q equals 0.02, Q equals 0.04, do the copy function. So that copy function saved me some trial and effort, but I had to hand enter these numbers 49 times. So just copying out this spreadsheet, be prepared. This may take you a couple hours. This may be some grunt work. Find some mindless TV show or music or something that you can watch or listen to while you're doing this mindless work. Be prepared. There's going to be a bit of grunt work involved in this. Okay, so you're going to calculate the likelihood function for 49 times 49 different values of lambda and Q. 49 times 49 equals 2,401. So you're going to have to compute the likelihood function 2,401 times. Okay, I want you to look through that, find the one that maximizes. Okay, one of those is going to be best. Write down the lambda and Q that are best. Okay, what you've done is called grid search now. Okay. So we're not doing Newton-Raphson, okay? We're not trying to find the lambda that has a derivative of 0. We're not even computing derivatives of the likelihood function, nor second derivatives of the likelihood function. We're just computing the likelihood function 2,400 times and looking for the best, okay? Okay, now, 7b, all right. Here is what's going to happen now. By the way, I said compute the likelihood. I'll give you a hint. It's actually, you might want to compute the log of the likelihood. Now, if you've maximized one, you've maximized the other. But remember, we're here in 7b, where, let's see, 7c. 7c, we're going to compute derivatives and second derivatives. And remember, for all those special formulas we have, those theorems we have, they all work on the log of the likelihood, not the likelihood. Okay. Now, define lambda star and q star as the two values that maximize your likelihood. Okay, I don't even remember what they're going to be. Let's say that they equal lambda. What did I tell you? Lambda was the ratio of the thetas. Is that right? Yeah, lambda's ratio. So, and we can remember from the Levitt-Porter paper, they said that when you're drunk, you're about 8 times more dangerous. So the ratio of the lambda is going to be about 1/8. So it's going to be about 0.12. Okay. That's what Levitt and Porter found. Now, I'm not telling you that I picked N0, N1, and N2 that will get that, but I'll give you hints. Probably going to be somewhere close. And then Q, okay, that's the proportion of drivers at any given time are drunk. And Levitt and Porter found that equals about 0.2. Okay. So let's say that those are the values that you find that maximize the data, given that N0, N1, and N2 that I gave you. Okay. I don't think that's actually R, but they're probably kind of close. Okay. So if we assume for the moment that's what they are, what I want you to do is, let's call that lambda, and this is Q, and then so we're going to have a lambda of 0.12, lambda of 0.14, lambda 0.10. So this is lambda star. I want you to consider the lambda just to its right, to its left, and then you have a q star, which equals 0.2, and then consider the one just above, 0.22, and the one just below, 0.18. Okay. So we've got 9 different values. Okay. For the 9 possible, list the value of the log likelihood function. Okay. So given each of these 3 values of q, these 3 values of lambda, compute the log likelihood for each one. Using the values of this table, compute the Hessian of the log likelihood function. Okay. There may be more than one way to do this. Okay. So the key is you're going to compute d squared. Well, the Hessian, first you're going to compute d squared L d q squared. Okay. So what you might want to do for that one is fix lambda at the optimal value. Look how L changes as you go from here to here. Okay. From Q equals 0.18 to 0.2. Okay. That gives you DL dq. Okay. And you get another derivative of that one to that one. So remember, this is like the positive derivative and negative derivative. Then look to see how the derivative changes as you go from here to here. And as you go from there to there, you're changing your value of Q by 0.02. Okay, so you're going to take the derivative from these 2 points minus the derivative from these 2 points, subtract those, take the difference, divide by 0.02. That should give you dl dq squared. Okay. You're going to do something similar with d squared little l d squared lambda squared. Okay. Let's set q equal to 0.2. Look at the derivative as you go from here to there. Look at the derivative as you go from there to there. That is varying lambda. Take the derivative. Look how those 2 derivatives change. So the derivative of those 2 points minus the derivative of those 2 points. By the way, remember to go that way. This one minus that one. Otherwise, you're getting the negative of that. But the derivative that you get from the derivative from those two minus the derivative from those two, all divided by 0.02, should get you the second derivative, should get you that point. Okay. Now, the final one, you need to get d squared L d lambda dq. Okay. There's various ways to do that. Let's see. One way, just look at the derivative as lambda changes, that derivative, okay? And then, okay, that's the derivative of L with respect to lambda. You could do it again here. So it's two different derivatives. The derivative of L with respect to lambda. You can look to see how those change, and that gives you the derivative of L with respect to lambda with respect to Q, okay? That's one way. There's another way. And by the way, dl squared d lambda dq, that should equal the derivative if you go the other way. If you first take dq, then d lambda. So if instead you did something like took the derivative from that value of little l versus that one, then do it again, that one versus that one. Subtract that derivative minus that derivative, divided by 0.02. I think that gives you this one. Whichever way you do it, you should get about the same answer, okay? And we've got theorems that say if your d is small enough and you didn't have this computer rounding error, then it should be exactly the same, okay? If you're close enough, I'll give you full credit. But you might want to try it a variety of different ways. Think about how to compute that second derivative. So you've got to get this, those two should equal each other. Okay. In fact, you might want to fix them. Do it the variety of ways. Make sure they approximately equal each other. Whatever you get, set them exactly equal each other. By the way, you could also do it this way. This might even be a little more accurate. Take the derivative when you go from here to here. And don't forget, when you're going, the likelihood value for these values of lambda and q, then taking the value of the log likelihood for these values of lambda and q, you've increased lambda by 0.04. So now your d equals 0.04. You've got to divide by 0.04 in this case. But try it. This, I think, may be the most accurate. Try it this way, and then look at that derivative. Okay, so now you've got two derivatives with respect to lambda. Then see how the difference between those two derivatives. Divide that by 0.04, and that should also get you dl d lambda dq. Okay, there's a variety of ways of getting that, the cross partial, I think they call it. So you've got to get those two terms, this term, and this term. Okay, that's your Hessian. Okay, once you've got that, 7D, using your answers to 7D, invert the matrix. So you have a 2 by 2 matrix. I told you in class, I don't remember the formula for inverting a matrix. By the way, my undergrad students, a lot of them can't do percentages. And the problem is because they've got their cell phones always with them with a calculator on it. They don't need to learn how to do percentages. This is just their generation. Something similar, my generation, we've getting used to R or MATLAB or Gauss. There's various matrix manipulation programs, because we've got a computer that has them on, we can use that to invert matrices. We don't have to do it by hand anymore. So I've forgotten how to invert a matrix. The good thing, it's on Wikipedia. Okay, so you're going to have a 2x2 matrix, A, B, C, and D, the 4 elements in the matrix. Wikipedia tells you how to invert that. Okay, invert that. That gives you the inverse of your Hessian. So remember, now that, you take the negative of that, that is going to give you what we call the variance covariance matrix. Okay, so if you put the upper left hand, the first term, the upper left hand term is this, the lower right hand is this, and then the 2 corner terms are those. Once you invert it, the inverted H, the negative of it, in the upper left-hand corner is going to give you the variance with respect to Q, variance of Q, the variance of your maximum likelihood estimate of Q. In the lower right-hand, it's going to give you the variance, the negative, remember the negative of your matrix. It's going to give you your variance of your maximum likelihood estimate of lambda. In the 2 corner cells, they should equal each other, or be very close to equaling each other. That gives you your covariance of your estimates between lambda and Q. Okay. All right, that's it. That is your homework problem. Okay. All right. So that, okay, is lecture 3.10. I'm going to do one more. 3.11, where I'm going to explain a little bit about the McFadden paper that we'll do in session 4. Okay, see you in that session.